Okay, hello everyone. I'm Sándor Laki from Eötvös Loránd University with Budapest, Hungary, and in our demo we present the idea of an AQM evaluation testbed with P4 and DPDK. So first of all, what is AQM? So active queue management aims at solving the problem of buffer bloating, and buffer bloating leads to increased queuing delay, and in this way it reduces the overall end-to-end performance. In the past decade, several AQM algorithms has emerged, including the traditional RAD or the delay-aware CODEL or the PI controller-based Pi or Pi Square. And so why we use P4 here? So in the traffic management subworking group, we have shown that most of the AQM algorithms can be described in P4 language. And to evaluate their performance, we need a comprehensive framework and evaluation testbed. And in this demo, we show the key concept and the first steps towards a comprehensive evaluation framework. And this framework is built on top of our DPDK-based P4 compiler called Tapas, which is the translator for P4 switches, and we will demonstrate its performance using the Pi AQM algorithm. So if you are interested in AQM and Tapas, just go to our demo booth in the lunch break, and enjoy the menu. Thank you.
Hi, my name is Arun Paneri. I'm Director of Engineering in Noviflow. I'm here talking about how we implemented gRPC, GNOI, and GNMI, and how we are moving towards the P4 runtime. So the company was formed in 2012 by keeping in mind that to provide SDN-based solutions to the market. We started with the NP5 EasyChip processor. We provided our NOS on top of this processor, which was fully programmable, match action pipeline based. And then later in 2015, we implemented gRPC server in our NOS. And also in 2017, we provided GNMI and GNOI, which was we showcased these two protocols in Google PlugFest in October 2017. Now we are moving towards the P4 runtime because we already have a gRPC server running in our switch, though it was based on the proprietary protobuf file. But now everything is getting standardized in the P4 runtime side also. So we are planning to provide a P4 runtime solution, which should be coming out in end of this Q2. And mostly we will be using like a Tofino chipset for providing this P4 runtime solution. Because of this expertise in the match action pipeline, we are also in the cybersecurity market. We are providing cybersecurity solutions for terabit switch scaling. I have two of my colleagues, Jeff Alpern and Kevin Austin here. Feel free to come to the demo room and we can talk about more in detail about how we are planning to provide the zero-touch provisioning and P4 runtime especially. Thank you.
Hello again, I'm Kalin Kaskaval from Barefoot. Given the number of talks talking about programming Tofino, you would think it's a walk in the park. Well, let me dispel that myth. It is actually pretty hard. Simon alluded a little bit to that. But what we do to help you is basically provide a set of tools around the compiler and the chip simulation to give you more insights into how the resources in the hardware are mapped, or in your program are mapped to hardware. We call this tool P4 Insight, and it works closely with the compiler. The compiler generates a whole bunch of information that allows you to actually see what happened to your P4 objects and how do they map to the hardware resources in Tofino, and then allow you to find all those last bits that you didn't think you would need, but do have your features. So I have a live demo of this in back. Thank you.
Hi, folks. I'm with MNK Consulting. So we have developed a P416 program that implements the Cisco ACI data plane. Currently, it's only supporting IPv6. But our program supports ACI data plane, NCAP and DCAP, policy enforcement, service graph creation, and IPv6 NDRA multicast replication. So ACI contracts map quite naturally onto P4. For example, an ACI policy can be implemented as a chain of P4 tables. Another example, service graph nodes, so your firewall, SSL offload, your load balancer, those can also be implemented using P4 tables. We do have a live demo of this program running on BMV2 Simple Switch with the Simple Test Framework, so please do check that out. And of course, the punchline here is that with something like the Tofino ASIC from Barefoot, we can easily get this program running on hardware, but also retain the ability to quickly add new functionality. So thank you.
Hi, everyone. My name is Peter. I'm currently a master's student at Cornell University, and today I'll be just talking briefly about our progress on an implementation of a software-simulated PSA switch. So PSA differs from Simple Switch in that it's more explicit and principled in its definition of a packet processing pipeline. So you'll notice that PSA actually defines an ingress deparser and an egress parser, which are things that were sort of implicitly assumed to exist for Simple Switch architecture, and this serves the purpose of, for example, allowing separate handling in ingress and egress pipeline. So for example, you might determine that a packet is a multicast packet in ingress, and then you might want to handle the clones separately in egress. And additionally, in PSA, we retain some of the really nice externs from Simple Switch. So for example, we still have counters, meters, hashes, checksums, and stateful registers, and et cetera. And so in the past 9 to 10 weeks, a group of undergrads and master students at Cornell, we have implemented the very basic packet processing pipeline for PSA, which is able to handle unicast and multicast traffic, as well as some non-feed-forward packet paths, such as recirculate and resubmit packets, without preserving in-switch metadata. And finally, we're actually currently able to use the counter extern and have some very basic P4 runtime support. So if you guys are interested at all in learning about PSA and how far we are, all of our code is in open source in behavioral model repository, and we'll be running a demo in the right-hand side conference room. Thank you very much.